Hey everyone, welcome and thank you for taking some time out of your day to join the wolfSSL live webinar Kyber ML-KEM Introduction presented by wolfSSL Senior Software Developer Anthony Hugh. My name is Cameron and I will be moderating the webinar. All attendees will be in listen mode only. If you have any questions, please use the Q&A box. We will host a Q&A session immediately following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you all to follow us on Twitter at wolfSSL, as well as our other social media platforms. Also, please feel free to email us if you have any additional questions. And now I'd like to give a brief overview before we move on to the technical presentation. Today, wolfSSL secures over 2 billion connections, and we have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we're extremely proud of. Since the beginning, our engineering team has developed several embedded security products, including WolfCrypt with DO-178 support, FIPS certification and FIPS ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, and a secure boot loader known as WolfBoot, as well as Java wrappers and JSSE support and commercial support for curl. And of course, all of these offerings are accompanied by thorough maintenance and support plans all the way up to the 24/7 level. We also do offer full service consulting. And now I'd like to turn it over to Anthony to talk about wolfSSL, Kyber, ML-KEM.
Thanks, Cameron. Yeah, so my name's Anthony Hugh. I've been working with wolfSSL for about 2.5 years now. And I happen to know quite a bit about post-quantum algorithms and post-quantum cryptography. So this is the agenda of what we're going to be talking about today. We're going to be, heading into a bit about motivation, the history of what's been happening with this particular algorithm, Kyber ML-KEM. We're also going to look at the generic KEM API mechanics, just because this is a kind of an unfamiliar thing. Even if you're really into cryptography, the way it works is a little bit different from other algorithms. We're going to get into a little bit of math. We're going to how to get started with Kyber and ML-KEM in wolfSSL. And we're going to be doing looking at some benchmarks, which are actually quite surprising. I think I'll be pleasantly surprised when you see our benchmarking results. And then we're also going to be looking at licensing and how you can use this stuff. At the very end, there'll be a Q&A session as well. Okay, so why do we need to do this this migration over to post-quantum algorithms? And the technical reason here is that there's a harvest now decrypt later threat today, right now as we speak. Our data could be harvested in its encrypted form, and then in the near or not so near future, sorry, it could be decrypted using a quantum computer. So you have to ask yourself, what is the lifetime of your data and how long does it need to stay confidential? And when we put up this topic, usually when you go out and you do the talk circuit, it gets kind of scary, and people kind of, bring out the harvest now, decrypt later as a boogeyman. And I don't really want to do that. So I'm going to, help you understand this by giving you a trivial example, the trivial case. And that case is my daughter's surprise birthday. I had to arrange her surprise birthday. So in that case, we have a secret and, we have consequences. So what was the secret? Well, it's that she's having a birthday coming up and we have a surprise birthday party for her. So what's the lifetime of the data? Well, it's until her birthday. So it's pretty short term. How long does it need to stay confidential? Until her birthday. And so what are the consequences of the data getting into the wrong hands? Well, she's not surprised anymore, but she's still pretty happy. She still gets her birthday party. So, as you can see, this isn't really a good case for needing a quantum computer, but you can use this kind of framework to apply to your own data. Your data has to stay confidential for a certain amount of time. Sometimes that's due to regulatory needs. And what are the consequences if you don't keep it that secret that long? Well, some of the consequences might be written into laws and litigation and other things like that. And if you're doing a military application, well, things can get really catastrophic. So I don't really want to get into that because you know your data and you know your use case better than I do. So just it's something that you need to think about. Now, the other motivation here is the CNSA 2.0, which stands for Commercial National Security Algorithms 2.0. And this is guidance that's given out by the NSA. The NSA basically kind of, I wouldn't say controls, but they give guidance to other government agencies to what they should be doing and what they should be using in terms of cryptography and security software. So here we are in 2024, and at 2025, for software and firmware signing, you're already supposed to be having this in post-quantum cryptography as an option in your in your in your products. This goes true for web browser. This is also true for web browsers and servers and cloud services. So, this is pretty. It's pretty soon. It's coming up. It's we're at the end of the first quarter of 2024. So 2025, you're supposed to have this post quantum stuff, these post quantum algorithms on by default. So let's go a bit through. I don't really want to go into all the details that are on this slide. The details here are for people who watch the recording and really want to, they can pause the recording and dive in here or request the slides. But really quickly, it started in 2016, and the whole standardization competition ended in 2022, and now we have our draft FIPS standards. I believe the name of the document is FIPS 202, and oh no, sorry, FIPS 203. I got that wrong. Yeah. So and that's a draft. Now that draft is supposed to get solidified by the by this year, sometime this year. I'm not sure. I've heard rumors that it'll be sooner than later, but I don't know exactly when. So yeah, let's look at the artifacts here of these things. So when you look at it, there's a decapsulation key and a ciphertext, and those are the things that are going over the wire. So those are the sizes of artifacts that really matter. Sure, the encapsulation key matters, but that it's not actually being sent over the air or wire. When you look at the decapsulation keys and ciphertexts, typically they're actually quite large compared to what we're used to. If you're going to go with the most secure version, the most secure parameter set for ML-KEM, you're looking at sending 3K one way, and then about 1.5K. So yeah, we're looking at almost 5 kilobytes going back and forth, and that's just to establish the TLS connection. So that's a lot of data going through just for the handshake. Now, so but the key here is that the performance, the execution is very good. Key gen, encapsulation, and decapsulation are really fast. Oh wait, sorry, I made a mistake. I said the decapsulation key was going to be going over the air, but it's not. It's the encapsulation key that's going over the air. So yeah, at the very for 1020 for the 1024 for ML-KEM 1024, that's going to add up to about 3 kilobytes of data going over the air. So while performance is very good, if your transmission medium is very slow, then that could eat up the performance gains that you're going to get, and you are going to get performance gains. So yeah, so here we're going to talk about the mechanics of what's going on. So generally speaking, there's a server that's waiting for a client to give it an initiation message. And so what happens is the client would do a key gen, and then the key gen would generate the public key as well as the private key. But then the public key would get sent over the air to the server. And then the server would use that public key to do an encapsulation. And the result of that encapsulation would be a shared secret and a ciphertext. The ciphertext would then be sent over the transmission medium to the client, and the client would then decapsulate that ciphertext. What would result is the same shared secret that the server has. So both sides now have a shared secret. That shared secret can be used as input for input into a KDF or used on its own as the secret within a symmetric cipher such as AES. Yep. And so that's how the key exchange actually happens. I note that this is fairly different from ECDHE, where in ECDHE, you just sort of, both sides just send up their own public key, and then there's a derive operation. So now we're going to not get into some math. So I should preface this with the fact that I am not a cryptographer. I don't, I'm a software developer. And so for me to talk about the underlying math within Kyber and within lattice-based cryptography would be inappropriate at best, and I might make a mistake and mislead you at worst. But we do have an excellent past guest webinar with Professor Douglas Stabila from the University of Waterloo, where he explains the ins and outs of the math of Kyber. So the link to that webinar will be available at the end of this presentation. And it's on YouTube, so it's recorded, so you can go back and watch it. Okay, so for anyone familiar with wolfSSL, this will look pretty familiar. If you want to get started, the first step is to download the source code for wolfSSL at www.wolfssl.com/download/. So then you'll get the .zip file. If you unzip it, cd into it, and then do a /configure --enable -experimental, then --enable -kyber equals all. That'll give you that'll turn on all the macros that are needed for being able to use Kyber. If you do a make all after that and a make check to make sure that everything's in order and all the tests are passing, that will get you to the kind of ready position for working with this algorithm. So we actually have a server and client example. So when you look at our server command line, in order to run the server, this command line is all you need. And it requires a little bit of explanation. So -v4 specifies that you want to use TLS 1.3, and --pqc Kyber _level 5 specifies that you want to use Kyber 1024 as the key exchange within TLS. So the group basically, in the key share extension of TLS 1.3, you will use a Kyber level 5 public key and ciphertext. Now, on the client side, it's the same thing, right? So examples /client /client -v4 -pqc Kyber underscore level 5. And underneath that command line is the output that you'll see, specifying that you are indeed using Kyber level 5. And it just so happens that your Cypher suite is TLS AES 128 GCM SHA 256. So we're about to get, I'll be showing you some benchmarks on my machine, but that we did on a few machines that we have here. But before that, but really those benchmarks aren't really important because you really want to know what benchmarking numbers you're going to get on your machine. So after you've built wolfSSL, you can just run the benchmarks and you'll see, and that's as easy as just typing wolfcrypt/benchmark/benchmark, and it'll just execute the benchmarks for all the algorithms that we have. And of course, if you have Kyber enabled, it will do that one too. So, okay, so it's important to note that we're looking at our implementation. Previously, we had done an integration with liboqs, as well as an integration with the PQM4 project for, what is it called? For the ARM Cortex-M4 hardware. But now all these benchmarks are our own Kyber implementation. Okay, so as you can see, Diffie-Hellman is by far the time hog here. It's fairly slow. But when we look at SecP256R1 and compare it to Kyber 512, Kyber does very, very well. And you can see that that SecP256R1 is actually comparable in time to Kyber 1024. Note that the numbers on the left don't really matter, because this isn't your machine. You're not necessarily using an Apple M1 Pro at 3.09 gigahertz, right? So, but what really matters is the comparison of the the relative proportions in time. Now, what I said was it was 256R1 is comparable to Kyber 1024, but if you really think about it, you're supposed to be comparing 256R1 with Kyber 512 because that's where the security equivalences are. So with that in mind, Kyber is doing quite well. It's taking up very little time and performing very well in its operations. So this is on my machine. These benchmarks were taken on my machine here that I have. This is an 11th gen Intel Core i7. Running at 3 gigahertz. And again, DH is crazy huge, but what's really interesting now is that we can compare SecP256R1 with Kyber 512. You can compare SecP384 with Kyber 768, which is the correct comparison. And you can see that SecP521R1 and Kyber 1024 are just night and day, right? So when you're using Kyber, you're actually going to get a performance improvement, not a performance hit, which is what a lot of people had expected. They had expected that these would be slower algorithms. And on another platform, which is the ARM Cortex-M4, I happen to have a Nucleo F446ZE sitting on my desk right now, and we ran the benchmarks for our implementation against that. And unfortunately, for SecP256, we only took benchmarking numbers for SecP256. For Kyber, we took all three. And as you can see, Kyber doesn't do as spectacularly as it did on the other platforms. And that's probably because the artifacts are larger. And so if the artifacts are larger, there's probably a lot more memory churn and memory access. And so that probably slows it down. Because on a microcontroller, you would imagine that memory accesses are probably a bit slower and happen at smaller sizes. Now, To get back to these numbers though, these look really, really good. But like I said earlier, the artifacts are larger. So these gains could very well be destroyed by a slow transmission medium, or not just that, if your protocol underlying protocol requires that you have to packetize something, then that can really, really slow you down. So while execution performance is great, you have to take that with a grain of salt because of the large artifacts. There we go. So here's some optimization flags. Here at wolfSSL, we're really into optimizations and architecture specific optimizations as well. So we have optimizations for Intel, for AVX 1 and 2. We have Intel speedups. Notably, you can tie into the crypto callbacks. So for what is it called? Kyber has underneath it other cryptographic components to it. So it's using other algorithms. And so what you can do is tie into hardware implementations by tying into our crypto callbacks, so that you can get other speedups depending on your platform. We also have Kyber small and we also have stack optimized flags. So if your stack is small, you can turn on wolfSSL_small_stack, and it will try to minimize the amount of stack usage. Of course, that usage goes to the heap, so you got to make sure you have enough heap space as well. Okay, so you're a customer and you want to use ML-KEM in your commercial software. Can you do it? And the answer is yeah, as long as you have a support plan with us. So if you have support, then go ahead and use it, try it out. For now, experiment with it. It is not yet standardized, and so we do not suggest putting it right into production right away. But yeah, we always encourage experimentation. If your support plan has expired, then what are you waiting for? Why don't go reach out to your business director and have a conversation with them, and we can figure out where to go from there. As promised before, here are some links. There's that link to the YouTube webinar. We have in our wolfSSL manual an appendice called Appendix, I think it's not ABCD, I think it's Appendix E. And it talks about our post-quantum, how to get started with post-quantum algorithms in wolfSSL. Importantly, we have not updated it yet to talk about our own implementation, but that update will come soon. And I also linked to the initial draft of FIPS 203, which goes into a lot of detail about the algorithm, which I didn't do because, again, like I said, I'm not a cryptographer, I'm a software developer. So if you want the real details there, that's where you go. All right. Cameron, I was wondering if there are any questions from you.
Yeah. Hey, thank you, Anthony. We do have a couple questions here. Starting off, is there or will there soon be support for AES 192 or 256?
AES 19, there already is support for those within wolfSSL for sure, because I know AES 256 is required for TLS 1.3, and so that is already there. Yes.
Awesome. Cool. Next here, do you also have a benchmark for Curve 25519 versus Kyber 512?
I can get it. Yeah. More importantly, my numbers won't reflect your platform. So you can enable, when you build wolfSSL, you can add in the configure command line -- enable I think it's curve. Yeah, curve 25519. And then you can run the benchmark on your machine and it will automatically give you benchmarks for curve 25519 right beside Kyber, KEM. But if you want me to run them for you, I'd be happy to. Unfortunately, I don't know who asked the question, but your best, if you want those, if you want me to run those benchmarks, you can contact me at support@wolfSSL.com, and I would be happy to run those benchmarks for you and give you those results.
Awesome. Next here, can ML-KEM be used statistically, or is it only appropriate for inferior use cases?
Oh, static versus ephemeral, right? That's really
Ephemeral, my bad.
important. So the truth is that, again, this is a question for a cryptographer to answer. That said, um, that said, I I know the answer, but I don't know the in-depth details of the answer. And the answer is that it has the Fujisaki Okamoto transform as a step in the algorithm, and so it's appropriate to use it statically. Now that said, what does that really entail? What does that really mean? You need to talk to a cryptographer to really get the gist of it.
Awesome. Next here, what version of wolfSSL is this in?
Oh, currently it's in on our GitHub master branch. You can use this, or I believe 570, which is our latest release, has this. So if you go to our wolfSSL.com/downloads, the current download is 5.7.0, and you can take that down.
Awesome. Thank you. Next here, are you planning on expanding FIPS validation for ML-KEM and ML DSA?
So that's a great question. FIPS is something that is near and dear to our hearts. When it comes to FIPS 140-2 and FIPS 140-3, we were always the first ones to get started on those. Now that said, currently ML-KEM and ML-DSA aren't even standards yet. They're just draft standards, right? So once that is actually solidified and the standards are stamped as standards, then I would imagine NIST would go into creating FIPS validation rules and regulations around ML-KEM and ML-DSA. And you can bet your bottom dollar that we'll be the first ones there for it.
Awesome. A couple more here. Are you planning to add PQ algorithms also for the certificate validation step, e.g., using dilithium or Sphinx?
Sphinx. Yeah, so we already have Sphinx Plus integrated into WolfCrypt. Sphinx Plus is only integrated at the API level just so that you can do keygen, just so that you can sign and verify, sorry. For Dilithium and Falcon, we actually already have both of those integrated via an liboqs integration. And so we already support a fully quantum safe TLS 1.3 connection, as well as DTLS 1.3. So what it is you would first build and install liboqs on your system, and then you would build wolfSSL, which would then link against the liboqs implementation. And then I didn't show it here, but you would then generate dilithium certificates or Falcon certificates, and then you could have a TLS connection using that. And yeah, it's pretty sweet because there is actually, in order to enable in order to enable these two algorithms, you don't actually have any application code change. We just look at what the certificates are, and then we go to town on that. So it's really, really convenient for you as the end user or customer.
Awesome. Thank you, Anthony. Next here, have you implemented a hybrid ECC plus ML-KEM mode?
Yes, we have actually. That's a great question because I actually did it myself. So what we did, because FIPS is so near and dear to our heart, we took the ECC NIST curves and hybridized them with ML-KEM. So what we support is P256 hybridized with Kyber at level 1, um, P384 with a hybrid. We P384 hybridized with Kyber at level 3 and P521 with Kyber at level 5. Moreover, in our wolfSSH product, we also support Kyber level 1 with P256. And we're thinking about doing we've actually blogged about it and we're working on X25519 hybridized with Kyber. But that's in our Wolf SSH product.
Awesome. Cool. Thank you. Next here, will you write your own dilithium and Falcon eventually for inclusion in Wolf Crypt?
Yes, we'll be doing our own implementations of dilithium for sure. Falcon as well, although I don't know the timelines on these things. Of course, we did Kyber first because of the harvest and decrypt kind of urgency. Those are threats that are there today, now. In terms of authentication, there is still kind of a need and an urgency there, but it's not as deep as for Kyber. But yes, we will eventually be doing our own dilithium and Falcon. And if you want that accelerated, let us know. Give us a shout at facts@wolfSSL.com, FACTS@wolfSSL.com, and let us know. You would like to see our implementation of dilithium and Falcon. And we can the more customer interest and demand there is for that, the higher we can prioritize it.
Thank you. All right. Next, once you bring in ML-KEM, will Kyber still be in wolfSSL?
So that's an interesting question. Kyber was the name of the algorithm during the competition. So once ML-KEM is officially standardized, we don't actually foresee anyone using Kyber. And the reason why is it's just like Rigendale and AES, right? Nobody actually uses Rigendale anymore. It's all AES. So from that perspective, we're probably going to be doing a rename from Kyber to ML-KEM at some point. When we bring in ML-KEM, we're probably going to be renaming it instead of putting it beside Kyber and leaving Kyber there.
Okay, thank you. And this one kind of goes along with that question. What are the differences between Kyber and ML-KEM?
Okay. So I'm gonna have to preface this again with the with the caveat that I am not a cryptographer, so I'm not really qualified to talk about this. But from a very, very high level, so I can't get into any detail because I'm not qualified to. I can tell you a bit about it, but if you want to see some details, the FIPS 203 document, page 2 of it goes into a fair amount of detail about the differences. But from a high level, it's basically a change in the format of the shared secret. They simplify the Fujisaki Okamoto transform, which I spoke of earlier. They actually added a requirement for NIST-approved randomness generation, so your entropy. So they removed an initial hashing that mitigated flawed randomness generation, like flawed entropy. And also they added checks for bad input data. And so that's very general. I'm sorry I can't get more into detail. I can't give more details about that as I'm really not qualified to.
Awesome. Well, cool. That wraps up our Q&A session unless another one floods in here. But yeah, thank you, Anthony, for hosting an informative webinar, and thank you for everybody for taking some time out to join the webinar. I will be sending a copy of the webinar and can provide PDF slides if needed. Just look out for my email. It'll be cameron@wolfssl.com. And please don't forget to follow us on Twitter at wolfSSL, as well as our LinkedIn and YouTube channel. If you subscribe, you'll get a notification immediately when this recording is uploaded. If you have any questions that come up later, shoot us over an email to fax@wolfssl.com. Thank you again, and we will see you next week.